presentation, and the second one is going to be live here in the conference room. Okay, the first one is it's a presentation by Gregor Byrne from he's in Canada, and maybe we can show everybody to say hi. And probably during the presentation I'm going to face the laptop so he can see. Okay. Okay. The work is about a new approach for an algorithmic composition of rhythm and meter for sound, and it's a piece of software called chunking. So where we are going to hear Gregor to tell us about it. Okay. What's it gonna move this? Okay. Don't break anything. Okay. Okay, start when you want. Okay. No, sí.
Hi, my name is Gregor Byrne. I'm professor in music at the University of Lethbridge, Alberta, Canada. I would like to talk to you today about chunking, software approach for algorithmic composition. Chunking contains 23 different functions for the creation of musical rhythms. In this talk, I will be concentrating on the creation of musical sentences. Chunking contains algorithms for integer partitions. These are all sums of positive integers that are contained within a particular integer. For example, 10 contains the sum 1 plus 2 plus 3 plus 4, or the sum 3 plus 7, or the sum 6 plus 2 plus 2. These sums are of particular interest for the generation of musical rhythms. Furthermore, chunking implements the Boris-Wheeler transform and its inverse transform. I also developed a new short-time notation for rhythm that is based on the use of single ASCII characters, which can be typed very quickly by the computer keyboard. Other algorithms come from the area of combinatorics of words, and these include bracelets and Christoffel words. In combinatorics of words, a word is a finite or infinite sequence of letters taken from a finite alphabet. Finally, we also have Ferri sequences, which deal with proportions and subdivisions. How do all those algorithms relate to music? The integer partitions are used to structure musical sentences. By this we mean that the integer partitions define the lengths of the individual parts of a sentence. Looking at the lowest level of the sentence algorithm, we will see similarities with the non-isochronous meters that have been proposed by Justin London. The non-isochronous meter is built upon beats that are of different lengths. Usually there are beats that are 2 or 3 pulses long. We also find that forces of impulse and resolution play out in the opposition between those beats that are either 2 or 3 pulses long. Musical impulse can be generated in very different ways by using melody, harmony, or rhythm. Once an impulse has been inserted into the music, it usually calls for a corresponding resolution, very similar to the act of breathing in and breathing out. One can find many asymmetric groupings in 2s and 3s in the rhythmic patterns of Turkey and Eastern Europe. Here is an example of a non-isochronous meter. Note the circular structure and note that we can step in at any point in order to have variations. A sentence can be regarded as a concatenation of such patterns. the sentence is built on a hierarchy of elements. The sentence is subdivided into phrases, which are further subdivided into patterns, and finally into chunks of rhythms. In this example, we have a sentence of 30 pulses in length, which is subdivided into two phrases of 17 and 13, and into patterns of 9, 8, 6, and 7 pulses. This view should give you another idea of how this hierarchical structure works. This is based on the same sentence structure, but with a different realization of the individual chunks. I'm using a special kind of partition, namely a partition into distinct parts. That means all parts have to be unique, and they have to be co-prime as well in order to generate good musical results. Two numbers are regarded to be co-prime if they don't share any of their divisors. For example, 2 and 3 are co-prime, as well as 7 and 12. We found that this feature has a direct influence on the musical result because of the level of impulse that can be generated. It also seemed beneficial that the numbers should not be too far away from each other. Therefore, we went for the smallest standard deviation within a partition. Here's an example of an entire musical sentence generated by this algorithm. Because integer partitions are always produced in descending order, chunking has to do some more work in order to form a musical result. By that we mean a process where musical material expands in order to reach a point of maximum, after which it has to decline. The longest part of a partition will always be found somewhere in the center, whereas the smaller parts are found at the beginning and at the end of the triangle. Now it's time to look at the lowest level of the musical sentence structure, the chunks of rhythms. At this level, chunking works with something we call templates. A template is simply a multi-set of 2s and 3s, representing durations in various orders. In order to better organize the large number of combinations that are possible, chunking uses 7 different musical categories of templates. Here are some examples of categories of templates. First, the resistor. 1 or more 2s are followed by 1 or more 3s. The idea here is that the flow of 2s is resisted against by the introduction of 3s, which form an opposition like. The release template is the opposite of the resistor. Note that these are just examples and that the number of 2s and 3s can vary. The arch template consists of 1 or more 3s surrounded by 1 or more 2s, whereas the catenary is the exact opposite. In the interesting growth pattern, a small group of 2s and 3s starts to expand. The decline pattern goes the opposite way. Finally, the alternating pattern is a simple repeat of a small group. The final step is to translate the chunks of 2s and 3s into actual rhythms. For this purpose, we have developed shorthand notation. It is based on a grid of 2 or 3 pulses. And as you can see in the left column of the table, simple ASCII codes are able to encode all the possible rhythmic chunks. Chunking produces 3 types of outputs. First, a C-song score file. Second, a script for Lilycom to render it into Western notation. And third, a list of all the shorthand rhythms that occur during the processing, saved as a text file. Chunking is a command line application that runs in a shell. It calls its different functions with the option M and further arguments. In this example, sentence is called with 2 arguments. 30 denotes the length of the complete sentence, whereas 2 denotes the number of phrases or patterns that are being generated. Here are some of the possible outcomes after executing this command. This is the C-sound score file. Here's the script that is needed for Lillipond. And this shows you an excerpt of the text file that is used in order to save all the rhythmic patterns that have been generated so far. And finally, the PDF file generated by Lillipond after inputting that script. Note the number of sentences and the variations between them. This is all being generated automatically by the same algorithm. And now a few demos in C-sound. These three little demos show hopefully how to use chunking's output to drive synthesis and sampling in C-sound. I hope you enjoyed the talk. Chunking is available as a GPL licensed open source software, downloadable at GitHub. Details here. Thank you so much for listening, and have a great rest of the conference.
Okay, thank you. I think we have plenty of room for questions. I'm going to put Skype in the screen. If we can. Yeah. So, anyone who would like to make a question?
Hi. Can you listen to me?
Yes.
Can you listen to me?
I can.
Yes. Okay, thank you. I have a question. Have you been doing some trying to expand this idea to polyrhythm, like homophony, zerophony, or things like that? I mean, algorithms that based on this rhythm patterns develop or construct some polyrhythmic textures? That's my question.
Yeah. Yes. This is very simple to do. And I hear my voice kind of delayed, but it's kind of sorry. Very difficult to do it with these because you have the fluids, of course, and you create several layers. Have different patterns in different key. So it is quite easy to develop arithmetic structures this approach. So I think polyrhythm a little bit maybe different than what is usually understood. For me, a polyrhythm already occurs in a set into a metric of frame per curve. Because you can shift the meter, you can interpret the rhythm structure to be a different metrical set. So, for example, rhythm that runs in 5/4 would suddenly run in 3/4 with the correct subdivision, and then the tension that is created against the new metrical structure is a polyrhythm, and so the metrical shift obviously very around and create interesting things. I tried with the third which I played to have a structure with these two different scores, but this is safe.
Okay, thank you. Do you want to ask any? Okay. Thank you.
I wonder if you have considered applying the same kind of combinatoric mathematics to the analysis and generation of melody.
Yes, indeed. I have incorporated I have incorporated the Lorenz-Miller transform and with this transform rhythms melody. The combinatorics of words are interesting for the compression of text file, for example. The Lorenz-Miller transform is used for that. If you take a word and put it into the algorithm and get a string out, which can be easily compressed, this is the purpose of the Lorenz-Miller transform. But then if you go back from that compressed kind of code backwards to the original string, you suddenly have an explosion of combinations because all the substrings of the input are generated in the inverse process of the Lorenz-Miller transform. So yes, with melody, you can do exactly the same thing as with the rhythmic structure. So the rhythms can be inputted into the Lorenz-Miller as well by using the shorthand notation, because the shorthand notation uses one character for chunk of rhythm. And the very compact code already. The first transform that allows two combinations of substrings and rotations as well. The Lorenz-Miller works on the principle of rotation. So when you have the word banana, for example, the last letter is sent to the front. So you have and then N is sent to the front, you have naban, and so on, until you are at the end of it. And the last column in it is the Lorenz-Miller word that is for compression. If you do the inverse, you all completely is possible substrings that are in the group, just melody that I've made lots of experiments in that regard by using short or melodic clips of entire motifs and selecting interesting parts from the combinatoric process that is generated by the Lorenz-Miller. So yes, I worked on the melodic parts as well, although this was not the focus of this talk. And I worked with the rhythmic layers on the other hand, with the same argument to combine those and generate material that is used for rhythmic position and for vocal position and so on.
Okay. Okay, thank you very much for your answer. I think we're on time to go forward to the next presentation. So thank you for being with us. Thank you for being.
Thanks for listening, and thanks for all. It's a big compliment to everyone.
Thank you.
It's so lovely to see you all.
Okay, thank you.
Okay, so the next presentation is going to be by Michael. We're going to set up the audio and video, so and then we go on with the presentation.
How long is this?
It's 25 minutes. Okay. Plus any questions. They told me to trust it. That's the video.
All right.
Okay. Okay. You have the microphone there. Is activated? Yes. Okay. Okay. So the presentation is going to be Michael, as I said, like Michael Goggins, and it's going to be involving HTML5 and how does that work with interactivity with system. Okay. Thank you.
Thank you. Thank you. And first, I'm going to just start off this piece, which I will also do during the break tomorrow. This is an improvisation. It has a fixed set of things you can do, which are fairly simple-minded, but then you can control them as they go along. So that's the beginning of this kind of performance. This is done with a combination of C sound and just plain old HTML5 that is standard in all web browsers now. So now I'm going to back up and start at the beginning of my talk, and maybe some of what I showed you will become sparking questions. So visual music, we have to understand what that is and where that comes from, how you use HTML with C sound, what are some of the trade-offs in this kind of visual music. There are many kinds, but I'm only going to talk about this kind. And then I present an example piece, and I'll show you a little bits and pieces of the code which is available online that solves some of these problems, at least for me, at least for this piece. Can you hear me okay?
Yeah.
Visual music can mean just a changing visual display, usually kind of abstract, that has a music-like evolution. Or it can mean music that has some kind of visualization generated from it or for it. Or it can mean a hybrid art in which you use software or algorithms to generate both the visual and the musical evolutions. That's what I'm doing here. And in particular, what I'm doing here is something that you control in real time. There obviously are many more examples of visual music that are created in a studio or with software and are just played back. It goes actually way back. The idea, people dreamed of everything we do long, long before there was any means of actually doing it. Here's the ocular organ. Then there was Walt Disney's Fantasia, which is really kind of the breakthrough in public consciousness of visual music, although there were experimenters in Germany and elsewhere for decades who were drawing and painting on movie film and all kinds of stuff like that. And then, of course, there were the light shows that people improvised for rock concerts. And of course, there was, for computer music, for me, the breakthrough piece was Circles and Rounds by Dennis Miller at the 2006 ICMC in New Orleans. This thing kind of blew my mind, and I guess that's why I'm doing this. If you're interested in this kind of art, I suggest you check out Dennis Miller. And then there's the demo scene where young men, usually young men, almost always, but not completely always, are trying to impress each other and potential employers by managing to code impressive pieces, music videos, visual music, abstract stuff in very tight coding constraints that run in real time. And these guys put our numbers to shame, as you can see. This is a demo party in Finland. Each dot of light there is the computer of a team or an individual who is presenting something at this show. Then there's processing and so on, and there's game engines, and there's live coding, all of which can do some kind of visual music. And nowadays, when people say video piece and electroacoustic music world, that really is some kind of visual music more often than not. What is HTML5? It's an international standard created mostly by companies, but not completely. It's essentially, it's a weird hybrid, and relative to what Joaquin was saying about the wonderful idyllic island where there is fragrant labor, the reality of these standards is very mixed. And we have companies, notably Google, Apple, Mozilla is a foundation, not a company. But they're the bosses. And what they say goes. They're open to suggestions, bug fixes, but they really kind of call the shots. But the work they have done so far has been excellent. As time has gone on, they have added capability after capability after capability to HTML. And it is quite mind-boggling. Essentially, the web browser is a math typesetting program, a word processor, a regular typesetting program, a database, several different kinds of databases, a network server, a JavaScript runtime, a three-dimensional real-time graphics engine, an audio synthesizer, a video playback and editing system, and processing system. All of this stuff has gotten into the web browser. And the beauty of it is that it's all backwardly compatible, just like C sound. Everything that ever worked pretty much still works. It's really impressive. So the things that are attractive for people trying to do visual music are the animated computer graphics and the high resolution audio. It doesn't have great latency. In theory, you can receive and process audio and play it back, but it's not really there in terms of latency and reliability. Now, a lot of people, including Stephen Yee here and Victor Lazzarini and other people, have put a lot of work into getting C sound to run in the browser context in various ways. So there's the C sound app for Android that I wrote based on the work of Lazzarini and Yee and other people who created the C sound Android library. There is C sound Qt, which now has HTML5 support. Then there's csound.node, which I wrote, which is an add-on for nw.js, which is essentially a web browser, the Chrome browser that doesn't need a web server. So it runs all of its HTML locally, which simplifies development. And some people use this for creating standalone applications that you just distribute like any other application. And then there's C-Sound web browsers, which has gone through where the C-Sound source code is actually compiled to run in the browser runtime, not as a separate program, not as a shared library, but actually as part of the JavaScript context. And that's mutated and morphed and gone from this to that, but it's going to end up as WebAssembly, which is another world standard run by the same bosses that will also be pretty good, I think. And it will replace these other things like in scripting in Pinnacle, even though Pinnacle so far has been better, but I think WebAssembly will end up better. So this raises technical issues. Visual music can be a very expensive proposition because it takes a lot of work, and work means people, and people mean pay. And there's another problem that so many people have tried to create these tools over and over again in different forms, for game engines, for scientific display, for every kind of reason. So people get in a little island and they can't talk to the inhabitants of the neighboring island, even though they're all doing the same thing. This is one of the reasons why I like C-Sound, by the way, is it's much more lingua franca. So I think that HTML5 is a potential solution to these problems. So much of the work has already been done. It's the same language for everybody. All the capabilities basically are there. There is not much that you get in a high-end game engine that you don't get from this if you really start pushing it. Now there are the artistic issues. Now, again, I'm mainly talking about fairly abstract, medium-length pieces of visual music, but there are sort of half artistic, half technical issues that arise. The visuals and the music can be composed separately, but in consideration of each other. I mean, the main issue is that they have to be synchronized. If you're looking at one thing and something else is sounding, it can be jarring. You want to avoid that. You want to have the things work together instead of against each other. So you can do them separately, which is what people did in the past. It's what Disney did in Fantasia. But this, of course, is not possible for an interactive piece. It's too much work. The visuals can come first and the music composed to match, or for interactive pieces generated from the visuals. Or the music can come first and the visuals composed to match, or generated from the music. But there's a bandwidth disparity. Even compressed visuals that are streaming run at about 300 million bits per second. And music that is streaming and compressed runs at, and I'm talking high precision audio, takes about 500 kilobits per second. So that's a 60-to-1 ratio. So if you tried to play everything that you saw, it would be noise. So you have to select the most meaningful parts of the visuals and only talk about them with the sounds. So you could go the other way and take the sounds and visualize them with various means, and there are many means of doing this, and that's usually what you see in music players. But the approach I took is to get some process going that is originally intended to generate visuals, and either use that to also generate the music or to sample the visuals and generate the music. So you can do this at a high level. In the scene graph, you have like a mountain that has on it a tree, that has on it a bird, that has wings and a head and a tail. That's the scene graph. So you can pick some level of this tree and associate that with music generation of some kind, creating a note or changing some parameter. Or you can do it at a very low level. You can take the raw pixels on the screen and somehow identify particular pixels or changes in pixels that you want to turn into music. And that's what I'm doing in the example that I started with. There is no scene graph. The fractal is generated directly as pixels. So that requires me to get the music out of the scene at a low level. So what I do is I look for a set of changes in the brightness of the pixels. And I map these events to musical dimensions, which I will show on the next slide. Still, the bandwidth is too high. We can throttle it either by more sophisticated feature detection or by sampling the visuals, and that is what we do here. I only look at every nth pixel. I don't look at all the pixels. I only look at some of them. So for mapping, it's very straightforward. Time is real time. Instrument is just a number. MIDI is for pitch. MIDI velocity is for loudness. There's just stereo pan for spatialization. So time is just time, and the simple math here shows you how the pixel dimensions, the x and the y, go into the musical parameters. So in the example piece, the visuals are generated using fractals that are controlled in real time by a few parameters. In this example, it's a GLSL shader. GL shader language runs at extremely high speed. It's a C-type language that has a runtime compiler in the web browser. This is another one of those amazing things that got into the web browser. And it runs, if there's a high performance graphics processing unit on the computer, the GLSL will compile for that target and run on that target. And it can run literally hundreds or even thousands of times faster than C code running on the general purpose CPU. It is really amazing how, that's the only reason we can do these crazy game graphics, because of this. So whatever happens in the visual context of a web browser ends up in a frame buffer of pixels. And so every so often I just grab that, and it's much slower to grab this thing than it is to compute everything in it, believe me. And then I run my JavaScript code to look at it and figure out what to do musically. So I'll show you the GLSL shader. First of all, here's the code for the piece. Notice that it is a web page. It is actually a C-Sound piece, but it's an HTML file. And it starts out with a regular HTML style stuff, including a style sheet. And by the way, the same code would work in C-Sound Qt and should work in C-Sound for Android app, and works in C-Sound.node, and with maybe some little tweaks, it should work in WebAssembly right in the browser. So, so then we have a bunch of scripts that are libraries, basically. So the spiffy little user interface with the sliders and what is that GUI. I use jQuery to find out what's happening in the GUI and fire off callbacks to control C sound and fractal. And there's some GLSL helpers and tiny color for doing math with the colors so I can find my pixels. Then there's silencio and chord space here are algorithmic composition code by me that when I was clicking on buttons and operating sliders to change the harmony, that's what's doing that. And then there's a sprintf thing, which is useful for printing formatted text. And then there's the table that you saw at the top that shows the time running and so on. That's just an HTML table. And then down here's the CSAT code. It's in a hidden text area, and it's got a whole 5 minutes left. Is that all? I had no idea it took so long. Okay, so here's the here's where C sound is brought in by requiring it from nw.js, and then it's just C sound. It has a lot of the same methods as the C sound API. These are the chords that I create from my chord space library, so I can monkey with them and send them to different chords. These are the default parameters for the GUI. These are the callbacks for handling the key presses and slider movements. And then the init function sets this all up. And here is where the GLSL shaders are created. So there's a vertex shader and a fragment shader. This is code just to compile the GLSL. And then I create the buffers I need, and let's see. So much code here. I can't remember where the math actually happens. It's very simple. It's just a few lines for doing the dots. Yeah. And here's where I take the pixels and I convert them. I get the colors and the brightnesses and whatnot, and I figure out what to do with them. And then I create an on event and an off event. An off event in C sound is an on event with a negative number. So that's very easy. And then I send the events using C sound. Here's where I do my mapping that you saw the math for. And then I round off the pitches to 12 tone equal temperament. And then I'm generating a little Java. In my library, there's a score object, so I'm stuffing all this stuff into a little score. And then I send it to C sound right here. And then I update my GUI. And this is stuff for binding external variables to the GLSL context. I know this is all going too fast and it's way too much, but that's it. So I'll take questions.
Great. Thank you for the presentation. I think we can take 1 or 2 questions. So anyone has a question?
Thanks, Mike. I was interested that you talked about this before, but
It's on.
oh, there's one. Just the idea that you mentioned about needing to filter visual data in some way in order to have a reduced amount of data stream coming into the synthesizer to work with.
Yeah.
Would it be something that you could look into kind of perceptual aspects, visual perceptual aspects, such as grouping of objects, rather than kind of looking at things from
Absolutely. Absolutely. And there are libraries that exist that you could use to do that. But this was my This was my second stab at this kind of a piece, so I was trying to keep it simple.
I guess it could get pretty complicated.
A lot of the code you saw is framework that can be reused. You can just take this piece and clone it and stick some new GLSL language or some new CSAP code into it. Change the GUI a little bit. It's not hard to make a new piece once you have the first one.
Thank you.
Any other questions?
Any questions? Well, very good. Just, I think it's related to what you said, but do you think it's possible and interesting to make the interaction directly on the drawing? Like
To draw.
Yeah, like interact with the drawings that are performed rather than a control inside. I don't know if it's HTML.
HTML can certainly do that.
But it's not easy. It's just to.
It would be fairly easy. Certainly could do that. Drawing.
Something that you can interact with.
That you can interact with. Yes, you would have to draw objects. You would not be able to just draw pixels directly. But then the objects, it would be vector graphics.
Yeah.
And then you would certainly be able to morph those, interact with those, apply splines, all that kind of thing, multiply them, divide them. Yeah, absolutely.
Okay, thank you. Okay, I think we're ready to go for the lunch break. So thank you everybody for being here, especially Michael. Thank you for the presentation.